Right. Now that um, we've looked at that layer normalization, we are going to look now at GELU and the feed forward. So we're going to do two parts in this one video. So we're going to look at the feed forward network with GELU. So GELU activation. If you have done neural networks, like I said, you know about ReLU. You probably know about ReLU, which is your rectified linear unit. But it is not common to see ReLU in these neural networks, these transformer networks, because they're large, they're very large and complicated architectures. So what you usually see is GELU or SWI SWIGLU, which is your switch gated. This is a switch gated linear unit, and then this is just Gaussian error linear unit. This, as the name says, it incorporates Gaussian linear units, and then this incorporates sigmoid. So Gaussian sigmoid gated unit gated linear linear units. They perform much better when it comes to activation than the ReLU. Um, so activation is essentially when you have an input, if your neural network is going to fire or not, especially in the ReLU case, if your neural network is going to fire or not. So you put in input into a formula or that activation that is there, and some calculation is done, and there's an output. So that output is the activation. So depending on which one you're going to use, the ReLU does not fire if you're putting negative values, because the ReLU graph itself is like this. So let's just say -1, -3, -2, -1, 0, 1, 2. This is the X. And this is the result, or this is the activation. And this is the activation. So when you apply the X to using ReLU, when you apply ReLU to the X, for ReLU, the results are like this. At 0, it will be when it's negative, when X is negative, the result will be 0. The neural network is not activated. But as soon as it becomes positive, it returns the result. It returns the result. So if it's 1, it will return 1. That is the definition of ReLU. The definition of ReLU. If it's 1, it will activate as 1. If it's 2, it activates as 2. If it's 3, it activates as 3. So it's a very linear. It's very linear here. But when it's negative, it just returns 0. So that network, or that node is not activated. The difference now is GELU. So GELU was found using. So GELU, I'll show you a formula, but GELU 0, 1, 2, 3, and then let's just say this is -3, -2, -1, 0, 1, 2. Let me see if I can draw it properly. So it does not touch 0. It becomes very, very small, and there is this part here that does this. So it is very nonlinear. So around -0.75, it dips down and then goes up like that. So this is your GELU. And GELU, it is defined as GELU is equal to X times this phi, X. But this phi, it is just what is called, it is the cumulative cumulative distribution function. It's a cumulative distribution function of the standard Gaussian distribution, of the standard Gaussian distribution. So that is that phi. But researchers for GPT-2, they used GELU, but they used an approximation to GELU. They found the approximation function through curve fitting, and they defined the approximation to be GELU is approximately 0.5 times the input x times 1 plus tan h uh, multiplied by square root of 2 divided by n multiplied by x plus 0.044715 times x cubed. So this is the approximation that they use. So in the original paper or in the paper for or in the training for GPT-2, this is the one that they used. So now this ReLU, as you saw, yeah, excuse me, I just want to pick up my pen. Yeah. So this ReLU, as you saw, it is a piecewise linear function. It is piecewise because it has two pieces that you can separate out the ReLU function itself. So so there's this piece here, and then there's this piece. So it's a piecewise function that y is equal to 0 if x is less than or equal to 0, and then y is equal to x if x is greater than 0. So it's a piecewise function like that. And but GELU is smooth, nonlinear, which approximates ReLU, but with a non-zero gradient for almost all the negative values, because here this gradient is 0, as you can see. It's a horizontal line, has 0 gradient. So this smoothness of GELU can lead to better optimization when we are training these models, because it allows for more nuanced adjustments than just if it's negative, it's going to be 0, no activation. Which ReLU does. That sharp corner in ReLU, this sharp corner is sometimes very nasty. Or it makes optimization harder, especially when you have these deep networks, when you have these many layers and all of them using ReLU, and it becomes quite complicated. So we are going to see this in code. And what we are going to do in code now is we are going to, so that's the GELU activation, but we are going to create a very small feed forward network. We're going to create a very small feed forward neural network, and that neural network is going to work like this. We're going to have input, we're going to have an input tensor, let's say with a shape of 2, 3, 7, 68, which is our embedding dimension. So this one will get into a linear layer, just a very simple linear layer. And linear layers, those are the ones that you characteristically see when people are talking about neural networks, the ones that are like this and very connected and all of that. Those are our linear layers like that. Those are just our linear layers. That's what we're going to do. So we're going to have a linear layer here. And the input for that linear layer is going to be this tensor that comes in, right? Which is this shape, 768. And what we are going to do, we are going to output, of course, 2, 3, and 3072. We are going to explode this dimension into 3072. We are going to explode it by a factor of 4. So which means here we'll have input, it will be 768, and we'll have here 3072. And after that, we are going to have our GELU activation, apply the GELU activation there. So the input for that GELU activation is going to be 233072, and then the output will also be 233072. So that's going to happen there in that layer, the layer with the GELU activation. So this layer here we have a GELU activation, and then we are going to have the third layer, the final layer, which is just going to be a linear layer. It's just going to be a linear layer, and that linear layer is going to have an input of 233072, and it will reduce that embedding dimension back to 768. So it will decrease it by a factor of 4 again, factor of 4. again. The reason why we're exploding it to this new higher dimension is we want to give the network capacity to learn even more complicated relationships in our data. So we explode so that we give it capacity, and then we just reduce it when it is done learning. So that's what we are going to do there. So let us see in code what this actually means in code. So let's switch to our Google Chrome so we can get into Colab. So in our code there, we have this GELU, and we've just defined the GELU as that approximation. So 0.5 times x plus 1 times torch, we get the tan h from torch times the square root of 2 divided by pi. Or I said n, I actually made a mistake. It's pi in my formula. It's supposed to be pi, not n, times what we saw when we were writing. So that's what we have here, right? So let's just plot it. Let's plot GELU, which is our GELU function, and our ReLU function from NN. We have our GELU and our ReLU function. When you're plotting them, you see this is the result of us plotting them, as we saw. That becomes like 0 here, but then becomes close to 0 here, and then it dips down and then goes up. For ReLU, it is 0 for all negative values, and then it goes up. So this is just plotting it, just so you can see. So now, this GELU, as you see, it is a nonlinear function, but with a non-zero gradient for negative values, except here where it then turns, where there's a stationary value around here where it turns, there is a small uh, area or around negative 0.75 where there's um, a zero gradient when it's turning. But that's just it. So let's create our feed forward network. Our feed forward network, we said we're going to have layers, right? We're going to have sequential layers. We're going to have the first sequential layer that's going to take in, it's going to be in, the input is going to be our embedding dimension. And then we are going to have 4 times, which is the output, as the output. 4 times that as the output. And then we apply our GELU. And then we apply a linear again, where the input is going to be 4 times our embedding dimension, and then it gets what gets out is just the embedding dimension itself. So we put it back to 768, like we said. And that's just the forward network. So we just return the layers there. Perfect, that's it. So for our embedding dimension, we know that our embedding dimension that we are dealing with according to our config is just 768. So let's create our feed forward network with the 3 steps that we showed. So feed forward, we are going to put our config. When we have our config, it's going to get the embedding dimension and create an object, this feed forward network, that is this setup. Now imagine we put an X that is 2, a batch size of 2, a number of tokens 3, and 768. We put it into our feed forward network. We expect the output to be 2, 3, 7, and 68 because here it gets exploded, yes, to 3072. GELU is applied, but then this last layer puts it down back to the output of the last layer. This output takes it back down to 768, as you can see here, 768. So our feed forward network is set up nicely. And that's just it. That's all we wanted to do there. We have added our feed forward network. So in our dummy, let me just go scroll the way back up so we can see how we are replacing things in our dummy. So in our dummy here, we were saying there are going to be some feed forward in our TRF block. They're going to be in the dummy transformer block. There's going to be a feed forward network, and so this is the part where we are building this block here. So we are replacing this dummy transformer block, adding something else again. We have already done the layer normalization. We've filled in this layer normalization. We are now filling in this part about the transformer block, adding the what we've just done now, our feed forward network, which is GELU. which is GELU activation. So that's what we wanted to do here. Let me just go scroll back again so we can show you. So this in the next video, let's quickly talk about shortcuts and why they're important or why they help this model stabilize. So we'll see you in the next video.